Today we are going to discuss on a topic which focus on how we can make blast furnace more efficient. Coke is a huge part of the cost of making hot metal and it's directly tied to CO2 emissions. So any improvement here is significant. We will be looking at two key strategies discussed in fascinating research paper. The role of highly reactive coke and use of a smaller nut coke. So let's get started. Modern blast furnaces are very different from their predecessors. They operate with less coke and high rate of pulverized coal injection. This new reality means old rules for coke quality do not always apply, especially when it comes to reactivity and size. The research we are looking at focuses on two big ideas. First, could using coke that react more easily, what we call highly reactive coke, actually lower the amount of carbon we need? And second, what happens when we charge a small size nut coke directly with the iron bearing material instead of in a separate layer? This has been shown to save coke and boost productivity, but the reason why are not fully understood. So let's tackle the first idea, highly reactive coke. The theory is that if coke react more radially, it could lower the temperature of what's called thermal reserve zone inside the furnace. This should improve how efficiently the furnace gases are used, which in theory means less coke is needed. However, the research shows it's not that simple. A lower temperature in this zone doesn't automatically mean less carbon is consumed. In fact, it might just shift a process called direct reduction to lower part of the furnace, which actually increase the heat requirement. It could also shrink the crucial indirect reduction zone. The bottom line from the analysis is that just increasing coke reactivity is not a silver bullet for reducing carbon consumption. Things get even more complex when you consider what else is inside the furnace. This study simulated blast furnace condition and looked at the impact of alkali like potassium, which are always present. They found that potassium vapor act as a powerful catalyst, speeding up the coke reaction. But here is the most interesting part. This catalytic effect is strongest on coke that has low initial reactivity. On coke that is already highly reactive, the effect almost disappears. Similarly, the ash and the char from pulverized coal also act as catalysts, accelerating the coke reaction, especially above 1100 degrees centigrade. But there is a twist. These same ash particle can form teeny sphere on coke surface, which might actually protect it from breaking down physically. So you have the dual effect, a negative catalytic impact and a potentially positive protective one. Now, for our second strategy using nut coke is just the smaller under sieve coke that's produced. Instead of being layered like normal coke, it's mixed directly with the iron bearing burden. The original hypothesis was that because the smaller coke is more reactive, it would get sacrificed by reacting with CO2, thereby protecting the larger structural coke from degradation. However, this paper states that both industrial trial and lab simulation have failed to prove this theory. So, if it's not about reactivity, what explain the positive effects? The evidence point to something else entirely. Improvement in how gas flow through the furnace and changes to the reduction process in the furnace shaft. This is the key takeaway about nut coke. The research found that mixing nut coke into the burden layer significantly improves the gas permeability of the furnace dry zone. In simple terms, it makes it much easier for gas to flow through the material. This leads to a lower pressure drop across the furnace. Why does that matter? A lower pressure drop allows operator to increase the blast volume, the amount of hot air being forced into the furnace without causing operational problem. And more blast volume directly translate to higher productivity. Calculation based on this principle shows a potential productivity increase of about 1.8 to 3.1% by using 10 to 20% nut coke. Amazing. To confirm this calculation, the researchers played a physical laboratory setup called a cold model to simulate the gas flow. They packed it with layer of sinter coke and sinter mix with nut coke to mimic the furnace condition. The results from this model were clear and confirmed the theory. As you can see in these, that pressure drop decreases significantly as more nut coke were added to the body mix. This effect was even more pronounced at higher gas flow rates, which are more representative of a real furnace. For a modern blast furnace with a high rate of PC injection, the model predicted an incredible productivity increase of between 7.7 to 12%. So, to wrap up, first, simply using highly reactive coke is not a straightforward solution for saving carbon as its effects are complex. Second, material like PC ash have a dual role, both catalyzing reaction and potentially protecting the coke. And finally, and most importantly, the primary benefit of using nut coke is not its reactivity, it's a significant improvement in the shaft permeability. By mixing 10 to 20% of nut coke with the iron burden, operators can lower the pressure drop, increase the blast volume, and achieve a substantial increase in blast furnace productivity.